Hello, my name is Anna Fausta and I would like to give you a short introduction to the hardware components of sensor nodes and their power consumption. So let's see first a typical example. This is the Zulertia Z1 sensor node, which is readily available on the market, and I selected it because it is a very typical sensor node. Its size is approximately fitting into your hand palm. There are some sensor node hardware which are much smaller, like in the terms of, for example, a small coin, but these are typically a little bit unpractical, especially for researchers who are trying out things and need a little bit more often access to the hardware itself. So researcher hardware is typically the size of the Z1, so nicely fitting into your hand palm. What are the components which are very, very typical, which you will find on almost each sensor node platform? First of all, it is the microcontroller. In our case, it can be very nicely seen here. It is the MSP430 from Texas Instruments, and it's also something which you see in many of those sensor node hardware. Then we also have a radio transceiver. The radio transceiver is probably one of the most important parts, together of course with the microcontroller, otherwise no work will be done here at all. But the radio transceiver now starts being something very typical for a sensor node, because all sensor nodes assume that they're not connected by cable to somewhere else, but they have a wireless connection to other nodes and to sync nodes, base stations, and so on. So of course the radio transceiver is an important component here. And the Z1 has also again a very typical radio transceiver, which is the CC2420, which is actually located here around but on the other side, so you cannot see it very well here. But here you can see the embedded antenna and the connector to an external antenna. Then we have also some sensors which are now spread here around. I will not make circles. Typically we have at least a couple of sensors, for example temperature and humidity, which are actually in the same chip, or we have sometimes also accelerometer or light and things like that. It is important to have at least a couple of sensors, even if you're actually working on the networking stack, because you would like to see whether with real data your applications and your protocols also work and how they behave, also in terms of power consumption. We will be back into that in a second. Then usually you also have external memory. The external memory is there so that you don't have only volatile memory in the microcontroller, but you can actually save also something in case, for example, your wireless communication is not working the way you expect. Typically you have at least a couple of megabytes, some have even up to 1 gigabyte. It depends on the hardware itself and on the setup. Then you have also the battery, of course. Usually all of these hardware can be run either on wall power, so by connection over USB, for example, but they should be also able to work on a battery. And the difference is actually huge. We will be into that soon. And of course, very important is the serial adapter. This is here, the USB slot here, which supplies power to the sensor node and which is used also for reprogramming and getting data out of the sensor node itself. These are the most typical examples. And in terms of power consumption, now we have to look a little bit more careful what consumes how much energy. Here I have a list of all of the components of Z1. And we see already, for example, that the microcontroller, here the first line in our table, actually doesn't consume a lot of energy. Even if it's active and working hard on some processing task, it has only a current draw of 1.8 milliampere. If it is sleeping, it is really low with approximately 5 microamperes. This is different for the radio transceiver. If you look into the radio transceiver, you see that it has actually 3 different states. This is not the same for all radio transceivers, but it is true for our CC2420. Here we have a receive state, transmit state, and sleep state or modes. And the receive one actually consumes more energy than the transmit one, even at the maximum power, which is 0 dBm. So what happens here is that you can make an analogy a little bit of how you're talking in a room. If you in a crowded room and you're trying just to speak and you don't really listen to anybody, you would like just to speak to somebody and you don't care whether he hears you or not, it is actually not that tiring task. You just speak, you don't care whether somebody hears or not. If in the same room, however, you're trying actually to listen to somebody and it's really crowded and with, in our case, interfered scenario, then it's actually very hard to listen and to demodulate the information which is coming to you. You can use that analogy simply to understand why the transmit state here, the transmit mode, needs less energy than the receiving mode. So, however, they're comparable, and the only possibility to save energy is to put the radio transceiver off when you're not communicating. And this is something which we do a lot in sensor networks to save energy. This is the so-called duty cycling, that we're putting the radio transceiver on sleep regularly because we typically are not interested in continuous sensor readings and continuous transmission to the base station, but we are only interested, for example, in the temperature reading every 10 minutes. So in the rest of this time, in the remaining 9 point something minutes, you can actually put the radio transceiver or even the whole node on sleep, which saves a lot of energy. Then here, for example, we have also the accelerometer, which is one of the sensors on board of the Z1. This has a very low, current draw, so we're not further interested in that. However, compared to that, also the temperature sensor, which is down here, is also not that problematic and dramatic. If you compare that to the radio transceiver or even to the microcontroller, it's okay. But the problematic case, which I would like to draw your attention to, is the external memory. This is something which programmers and beginners with sensor networks typically tend to ignore, that saving something to your external memory is actually almost as expensive in terms of energy as sending it out. This is probably just a misunderstanding, but that's why it is very important to remember that whenever you try to really save something to your external matter, you actually activate it, and this process is very, very energy hungry, and you should try to avoid it as much as possible. With other words, what people are doing is to make some sort of a volatile buffer with data, and only when this buffer is filled, then you transfer this data to the external memory, and you're not doing it every time you have some new data. And of course, you also try to send it out. Another important thing to understand about power consumption and energy management on sensor nodes is the so-called reference power for sensors. Here the idea is the following. Whenever you have a sensor, it actually typically compares the input power from the sensor itself to some reference value. And whenever the comparison is, it actually tells you what the temperature, for example, is. This reference value comes from the power supply of the sensor node. If it is wall power, there is no problem. The wall power will never change, or hopefully will never change, and so the reference value will be nicely fixed to some value. However, if this reference value is to come from the batteries, then you start getting into troubles whenever the battery goes down and cannot deliver the reference value anymore, the output power which it actually the sensor node requires. And this reference value is typically as low as that you can continue working for some time, even if the battery is not working optimally anymore and is being drained. But at some point, this will drop. So here is an example where the experiment which we performed together with the Technical University of Berlin some years ago was that we supplied a sensor node with a particular voltage, and we have measured the temperature output of the temperature sensor on this node. We didn't change the temperature, but we had the possibility to nicely change in step the battery voltage. And so what you can see here is actually very interesting. So in the very beginning of this curve, whenever the battery voltage is relatively high, 2.2 is actually already very, very low, but it still is high enough for the temperature sensor to work correctly. The delivered data, the sensor reading, is always fixed to what was the room temperature in fact, and that was around 25 degrees. However, whenever the sensor node voltage starts dropping, so here for example at 205 or very extremely here at 2, suddenly the reading goes up because simply the reference value is now incorrect. So it is comparing to something which is changing by itself, and this is what happens. So whenever your battery starts going down and cannot deliver the voltage which is actually required, you cannot rely anymore also on your sensors. This can be solved by hardware, by observing the voltage which is delivered to the microcontroller and to all components, but it is usually not done in cheap sensor node hardware because it's simply cheaper to not do it. So this component will cost you some money, and that's why we typically don't do it. So from that, what I would like you to remember is, first of all, that the power consumption of the individual components on the sensor node are very, very different, and you need to know which component needs what kind of a power in order to be operated, and you need to be very careful about which components are on and which you can put off, and put of course anything which you're not needing right now to off, to sleep mode. And the second take-home message is that you cannot rely on your sensor readings whenever your battery goes down. There is absolutely no security for you that the reading will be correct, and this is also one of the biggest challenges in sensor networking. Thank you very much.